All right, diving in today, quantum computing. Specifically, this quantum parallelism thing.
Yeah, it's a pretty wild concept.
Definitely. Our listener wants to get it, but, without the whole PhD in physics thing.
Makes sense.
I mean, their source material, dense, academic paper, all that.
Oh, yeah. I can only imagine.
Don't worry, listener. We'll handle the heavy lifting. Get to the good stuff.
Absolutely.
Basically, everyone wants to know, right? Can quantum computers solve, any problem instantly?
Haha, yeah, that's the big question.
Spoiler, nope, not instantly.
Not quite.
But the way they do work, mind-blowing, for sure.
It really is. The thing to remember is quantum parallelism, this isn't like anything we experience normally.
Right.
It's not just like, oh, doing lots of things at once, like your computer with a zillion cores.
Okay, yeah, so not just multitasking on mega steroids?
Exactly. It's deeper than that. Quantum parallelism, it's about, I guess you'd say, tapping into how weird quantum mechanics is.
Okay.
And using that to explore tons of solutions all at the same time.
Okay. So, say I've got a normal computer, even one with tons of cores.
Sure, yeah.
Each one's doing its own task, right? Like little worker bees.
I like that.
But with quantum, it's like one core suddenly becomes able to do what, countless bees would.
Pretty good analogy, yeah. And we're not talking a few thousand operations at once either.
Oh, no.
Imagine, say, 300 qubits. Those are the basic units for quantum computers.
300, okay, and they do more than my laptops. What, 8 cores?
Uh-huh. Oh, way more. 300 qubits, theoretically, could explore more states than there are particles in the entire universe.
Hold up. More states than particles in the universe. A lot to juggle at once. How does it even keep track?
That's where the superposition concept comes in. See, a quantum computer, it can exist in multiple states at the same time.
At the same time?
Yep. So it can explore tons of paths, like computationally, in parallel, like reading every book in a library simultaneously.
Whoa, okay. So it's not just how many possibilities, it's the way it explores them that makes quantum different.
You got it. Think about waves, right? How they come together. Sometimes they make each other bigger, sometimes they cancel out.
Like, oh, noise-canceling headphones.
Exactly. That's interference.
Yeah.
And that's key here.
But instead of sound, it's possibilities interfering.
Yep. By controlling that, we can guide the computation towards the answers we want, like almost directing a beam of light.
So, less like chaotic explosion of math, more like a very organized dance of possibilities, all working together.
Very elegant dance. And we choreograph it using quantum algorithms. The paper mentions this root of not gate.
Uh-oh, jargon alert. For us non-physicists, what's a gate even mean here?
Think of it like a basic operation, the
Yeah.
building block of how we compute. Like in regular computers, you got not gates, right? They flip a bit, 0 to 1, or the other way around.
Right, okay.
In quantum, we can use this root of not to do the same thing,
Yeah.
but in a way that uses that parallelism we're talking about.
So same result, just fancier way to flip the bit.
Exactly. We apply this root of not twice. First time, it puts the qubit into superposition. So imagine, it's exploring both 0 and 1 at once.
Not once, okay.
Then the second time we apply it, that's what uses interference to make sure we end up with the flip state, just like a normal not gate would done.
So instead of a direct flip, it's like quantum detour, explore all the options, then land on the answer we wanted.
Exactly. And the cool thing is we can actually see this process. The paper has these quantum data flow diagrams.
Diagrams, okay.
They show how much parallelism is happening throughout the calculation. Really fascinating to see it unfold.
Wait, so the parallelism isn't constant. It, changes as it's working.
Yeah. Several things cause that. Interference is one, like we just talked about. But there's other key features of the quantum world that come into play, too.
So interference is just the beginning. What else makes all this parallelism possible?
Well, for one, how probabilities work in the quantum world is totally different from what we're used to.
Probabilities. So, chances of something happening, right? Like rolling a 6 on a die.
Exactly. But in quantum systems, these probabilities, they don't just add up nicely.
Oh.
They can cancel each other out, or they can amplify each other.
That's weird. The chances of rolling a 6 can suddenly go down because of something else happening on a quantum level.
It is strange.
Yeah.
It all comes down to how quantum mechanics uses complex numbers.
Hold on. Imaginary numbers,
Yeah.
like square root of -1. What's that got to do with anything?
Huh. I know, it's a lot. But those imaginary components are essential. They let quantum probabilities act like waves.
Waves.
Yep, interfering with each other. So it's not just adding numbers, it's like combining waves that can either boost each other or cancel out.
Okay, my brain's officially hurting. So probabilities in quantum are like, what, a wave symphony instead of simple math?
Uh-huh. Love that. And this is why quantum parallelism is so powerful. We can actually manipulate these interfering probabilities.
To what, steer the calculation towards the answers we're looking for?
Exactly. It's not just blindly trying everything. It's about strategically controlling the chances of each possibility happening.
Okay, so that's interference and how it messes with probabilities. What's
Yeah.
next on the list of weirdness?
The second big thing is how we assemble these quantum bits, the qubits. Unlike normal bits, which are just 0 or 1, a qubit can be in both states at once.
Both at once, right? Superposition.
Exactly. And this leads to, well, an explosion of possible states, an exponential explosion.
Exponential. Sounds intense. So like add one qubit, you double the number of possible states the system can be in.
Precisely. And it's mind-boggling how quickly that adds up. With just a few hundred qubits, we're talking more states than atoms in the entire known universe.
So that's where the massive parallelism comes from. Each qubit's like unlocking a whole new universe of possibilities.
That's a great way to visualize it, yeah. Each qubit adds another dimension to our computational space, and that vastness, that's what lets quantum computers explore stuff way beyond what normal computers could even touch.
But hold on, exponential scaling, it sounds great in theory, but are there like practical limits? How many qubits we can control and all that?
Great question, and a huge challenge in actually building these things. You see, there's this thing called entanglement. It's the third key feature here, and it's this, well, spooky connection between qubits.
Entanglement, right. That's where, like, even if you separate two qubits by a huge distance, they're still linked somehow.
You got it. Like they share some secret nobody else knows,
Yeah.
and that lets us explore quantum states you just couldn't get with individual qubits alone.
Okay, so we've got interference, exponential scaling of qubits, and this spooky entanglement action going on. How do they all work together to make this quantum parallelism happen?
It's like this amazing interplay. Imagine like a vast landscape of possibilities. Each qubit's adding another dimension to this landscape. Then interference. It's like a sculptor, shaping the landscape, guiding us towards the solutions we want. And entanglement. Those are like bridges connecting distant parts of this landscape, letting us explore stuff that'd be totally unreachable otherwise.
All right, starting to get a feel for how powerful this quantum parallelism is. But there's got to be limitations, right? It can't be infinitely powerful, can it?
You're right to ask that.
Yeah.
And it leads us right into some classic computer science territory. Some of the fundamental laws there, well, they might apply to this quantum world too.
So we're going to see if the rules of the old game still hold up in this new, super weird quantum arena. Let's do it.
Limitations on quantum parallelism, huh?
Yeah.
Where did those even come from? I thought we were dealing with, like, universe-shattering levels of computing power here.
It's true. Quantum computers have insane potential, but they're not like magic wands, you know?
Right, right.
Even in the quantum world, there's some fundamental limits we run up against. Remember Amdahl's law from like way back in classical computer science? Vaguely. Something about how much faster you can make a task by just throwing more processors at it?
Exactly. Amdahl's law, it's a reminder that the speed up you get from parallelism, whether it's classical or even quantum, it's limited by the part of the task that has to be done one step at a time, serially.
Ah, okay. So even if you've got a zillion quantum cores all working in parallel, you're still stuck waiting for that one part that's like single file line.
Perfect analogy. It's like having this superhighway that suddenly bottlenecks down to one lane.
Oof. Yeah, I can see that.
And the thing is, even quantum algorithms, they have these inherent serial parts. Think about how we even get data into a quantum computer and then back out again.
Oh, right. Like translating between our regular world and the quantum one.
Exactly. That translation process, it's serial.
So even if the quantum calculation itself is blazing fast, we're still limited by how quickly we can feed it the data and then make sense of the results on our end.
Precisely. It's like having a super fast race car, but it's stuck behind a school bus.
Ugh, the worst. So Amdahl's law, still a buzzkill, even in the quantum world? Are we just stuck then? No way around it.
Well, researchers are working on making that whole input-output process more efficient. But it's a fundamental challenge for sure.
Okay, so it's not just about maximizing the quantum power. It's got to be a balance with, like, good design for the whole process.
Exactly. Every stage of the computation matters. It's not just about the parallel part. Now, Gustafson's law, that's interesting in the quantum context.
Gustafson's law. Refresh my memory.
It's all about scaling the problem size along with your parallelism. The idea is if you can adjust the workload so it takes full advantage of all that processing power you've got, you can get pretty close to linear speed up, double the processors, roughly halve the computation time.
So instead of trying to force a fixed size problem onto more and more processors, you're actually making the problem bigger to match.
Precisely. But here's where it gets really mind-bendy.
Hmm.
Does Gustafson's law even apply when we're talking quantum parallelism, which theoretically could be limitless?
Whoa, yeah. If we're dealing with like near infinite processing power, does it even make sense to talk about scaling the problem up to match that? Wouldn't that need problems of like universe-size complexity?
That's the challenge. We need problems that are not just parallelizable, but also have a complexity that scales well as we add more qubits. Like, imagine having this giant canvas, but needing to find the right paint, the right brushes, to actually create something that takes advantage of all that space.
So it's not enough to just have the horsepower, it's about finding the right racetrack to let it loose on.
Exactly. And that's a huge focus in quantum computing research right now, figuring out which problems are best suited for this kind of massive parallelism to actually make a difference.
Okay, so quantum parallelism, powerful, yes, but not a magic solve everything button. We need clever algorithms, efficient input output, and the right kinds of problems to really use it well.
Couldn't have said it better myself. We're still early days in figuring out how to best use this incredible technology.
You know, there's one more thing I gotta ask about, kind of out there, but the paper mentioned this many worlds interpretation. It sounds like sci-fi to me.
Ah, yes, the many worlds interpretation. It's a way to think about quantum mechanics where basically every time we make a quantum measurement or even just have an interaction, it causes the universe to split.
Hold on, every time a qubit flips or something, we get a whole new universe. Are we talking parallel universes here?
That's the gist, yeah. Each branch of this split represents a different outcome, a different path reality could have taken.
Whoa, okay. So it's not just that quantum computers are exploring many possibilities, but each one is actually playing out in its own separate universe.
It's a wild idea, for sure. Now, whether you buy into the many worlds interpretation or not,
Hmm.
it definitely highlights how mind-boggling quantum mechanics is. It challenges everything we think we know about reality.
Yeah, making me rethink my whole existence over here. Okay, so we've gone from mind-blowing parallelism to full-on mind-bending multiverses. How do we bring this back down to Earth? Like, what does it all mean?
That's where those quantum data flow diagrams we mentioned earlier come in handy. They give us a visual way to grasp how the parallelism is changing throughout a quantum computation.
Okay, diagrams, got it.
They show us the ebb and flow of those possibilities, how interference and entanglement are all playing together, like having a map to navigate this crazy quantum landscape.
All right, so let's get concrete. The paper uses two specific algorithms to illustrate this, right?
Exactly. First one's the Quantum Fourier Transform, or QFT for short. It's a key part of lots of quantum algorithms, and it really shows how parallelism can change dynamically throughout a computation.
Okay, QFT, got it. And then the second one is Amplitude Amplification, or AA. That one's used in search algorithms, right?
You got it. And what's cool is these examples, they teach us that it's not just about brute force exploration of every possibility. It's more about finesse, about control.
Okay.
It's about using those unique quantum features to, like, manipulate the possibilities and guide the computation where we want it to go, like composing a symphony of probabilities with each qubit playing its part.
A symphony of probabilities. I like it. Okay, I'm ready to see these algorithms in action. Let's take a look at those diagrams and see what this quantum symphony looks like. Okay, let's break down these algorithms. Quantum Fourier Transform first, the QFT. It's used in a bunch of quantum algorithms, so it seems like a good place to start. What does this QFT actually do?
Imagine you've got a signal, right?
Yeah.
Could be sound, light, even data in a computer.
Mm-hmm.
And you want to figure out what frequencies are in that signal. That's what the Fourier transform does. Breaks it down into all its individual frequencies.
Okay, yeah, I kind of remember that from some math class years ago, but the quantum version does it faster.
Way faster, yeah, for the right kind of problem. See, the QFT, it uses superposition and interference to analyze all those frequency components, but exponentially faster than we can do classically, especially when you have a ton of data to work with.
Got it. So let's look at this diagram. It's a bit complicated looking.
Can be a bit intimidating at first, yeah. But it's actually pretty elegant when you break it down. Each line, that's a different computational path. And how thick the line is, that shows you the probability of that path being taken. So we start with a normal classical input state. And then those first few gates, remember those are our basic operations, well, those create a massive superposition.
So all those lines spreading out, that's the burst of parallelism we were talking about. The quantum computer's checking out all the possible frequencies at once.
Exactly. But then, as we move through the QFT circuit, see how some of those lines start merging. That's where interference comes in.
Ah, okay. Like we're narrowing down the options, honing in on the frequencies that are most likely.
Right, the controlled operations in the circuit, they're like.
Hmm.
They manipulate the phases of these quantum states, causing that constructive and destructive interference. Like a filter, you know. It amplifies the paths that lead to the right frequencies and suppresses the ones that are wrong.
So the parallelism is actually decreasing as the computation goes along, but that's a good thing. Means we're getting closer to the answer.
Precisely. It's not just parallelism for the sake of it, it's directed, purposeful. And what's really cool is the amount of parallelism in the QFT, it actually depends on the input signal itself. If the signal has just one main frequency, we'll see a quick drop in parallelism. But if it's more complex, that parallelism sticks around for longer.
So the quantum computer is what? Adjusting how it tackles the problem based on what the problem actually is? That's pretty smart.
It is. All right, let's shift gears to Amplitude Amplification, the AA. This one's all about searching for a specific answer among a huge set of possibilities.
So like the classic needle in a haystack problem, but quantum style.
Exactly. And just like searching for a needle, you wouldn't just randomly poke around, right? You'd use some strategy, try to make your search more efficient. That's what AA does. It boosts the chances of finding the right answer.
Okay, makes sense. Let's check out the AA diagram. Lots of lines here, so it looks like we've got high parallelism the whole way through. But some lines are thicker than others. What's that about?
Good eye. The thicker lines, those show paths that are more likely to get us to the correct solution. The thin ones, those are less likely.
So why not just ignore the thin ones then? Why even bother exploring those paths?
That's where it gets interesting. Even those weaker paths, they might have low probability individually, but they're still super important for the whole algorithm to work. They contribute to the interference patterns, and ultimately that's what steers us towards the solution we want.
Ah, I see. It's like they're giving us little hints, and when we combine those with the stronger signals, it helps us navigate to the right answer. It's about the interplay of all the possibilities, not just the obvious one.
That's a great way to put it. And that's a key takeaway about quantum parallelism in general. It's not just about blindly trying everything. It's about that subtle, elegant interplay between all the possibilities, strong and weak.
All right, so we've talked about quantum parallelism, what its limitations are, and even seen it in action with these algorithms. It's been a pretty wild ride through the quantum world. What's the big takeaway? What should our listener walk away understanding about this whole concept?
I think the biggest thing is this. Quantum parallelism, it's a completely different kind of computing power. It's not just faster in the way we're used to thinking about it. It's a fundamentally different way to compute. One that takes advantage of all the strangeness of quantum mechanics to explore these vast landscapes of possibilities and solve problems in ways we're just starting to grasp.
It's almost like poetic, that by embracing the uncertainty, by exploring every possibility, we can find solutions that were hidden before.
It really is, and it opens up so many exciting questions. How is this going to shape our future? What new discoveries will it lead to? We've barely scratched the surface.
Totally. And who knows, maybe in some other branch of the multiverse, we've already got it all figured out.
Haha, now there's a thought-provoking image to end on. The possibilities truly are endless. Thanks for joining us on this deep dive into the fascinating world of quantum parallelism.